Alright, this is the Unit 13 practice exam. I'll go through here the multiple choice section pretty quick. So kinetic energy is most related to what? You should know this pretty well by now. We've talked about this for the last couple units. It's temperature. The temperature is defined as the average kinetic energy. Alright, if you increase the pressure on a gas and keep everything else the same, what happens to its volume? They're on the same side of the PV equals nRT equation, so they're inversely proportional. So if you increase pressure, you decrease the volume, so that it's B. If you increase the temperature of a gas, what will happen to its pressure? These ones are on opposite sides of the PV equals nRT equation, so they're directly proportional, so they go up together. So that's A. Number 4, the process when a gas spreads slowly through another gas. This one is called diffusion, and that's from that first set of notes that we had this chapter. So that's actually technically you can have a gas spreading through other things. A gas can spread through a liquid or through a solid. It happens more slowly, but it's all called diffusion. Number 5, which of the following will increase the pressure of a gas? So the answer here is A, faster moving particles. If it's faster moving particles, they're going to hit the sides of the container harder, and so they'll transfer more pressure there. Increasing the volume would actually lower the number of collisions because there's less particles per unit volume, basically. Having less collisions, of course, means less pressure, and less gas particles is going to mean less collisions as well, so less pressure. Number 6, which of the following cannot be plugged into a proportionality law comparing temperature and pressure? It's C. Celsius, because Celsius is a relative temperature scale, can't be plugged into proportionality equations. It has to be Kelvin. Kelvin is the absolute temperature. 0 Kelvin means 0 energy. 0 Celsius doesn't mean 0 energy. It's just the freezing point of water, and so we have to have it in the absolute temperature scale. We have to have it in Kelvin when we're plugging into anything. Number 7, when you increase the temperature of a gas, what happens to its density? This comes from that first set of notes again. If you're increasing temperature, density is going to decrease, and then the gas is going to rise up. So for that one, think of like a hot air balloon. Density goes down, so the thing rises. Number 8, it says if you double the volume of gas and decrease its temperature by 1/2, what happens to the pressure, assuming everything else is constant? So I would break this down into two things. We're looking at what happens to pressure. So first think of doubling the volume. If we double the volume and pressure are inversely proportional, so doubling the volume cuts the pressure in half. Okay? And then if we look here at the second thing, we're reducing the temperature to 1/2. Okay, temperature and pressure are directly proportional, so decreasing the temperature to 1/2 also cuts the pressure in half. And so what we have is the effect here is we're cutting it in half, and then we're cutting it in half again, which means the pressure is going to be cut into 1/4. On to these problems down here. We're going through, watch the units on these if you're plugging it into PV equals nRT. Also, the proportionality laws, make sure that you're watching the units there. The units you put in are the same as the units that you get out. So this first one is just a PV equals nRT equation. We've got all the information. We just need to plug it in. It's not asking us for a before and after sort of situation. It's just asking us to plug things in. So it says we've got 2.35 moles of gas and a pressure of 890 millimeters of mercury. This 890 millimeters of mercury is not the right units to go to PV equals nRT because R is 0.0821 liter atmospheres per mole Kelvin. So we have to convert the 890 millimeters of mercury to atmospheres. So this is the way that works. We start here with 890 millimeters of mercury. Okay, and then if you look up at the top of this page, there's a conversion factor. It says 760 millimeters of mercury equals 1 ATM. And if that's the case, then we're going to get 1.17 ATM out of that. Okay, and now we can plug that into the PV equals nRT equation. So pressure 1.17, volume 4 liters, equals N, the number of moles is 2.35, 0.0821 for R, temperature is what we're trying to get. We go through, calculate that there, you get temperature equals 24.3. But you have to be careful again here because the temperature that comes out of PV equals nRT is temperature in Kelvin. I asked you for the temperature in Celsius here. You know that Kelvin equals Celsius plus 273. All right, we want Celsius though, so Celsius is going to equal Kelvin minus 273. All right, which means that we end up here with D, negative 249 degrees Celsius. Problem number 2, this one is a proportionality equation. It gives us here an initial pressure, it gives us an initial volume, it says the pressure is increased to 100 kilopascals, and it asks us for the new volume. So the proportionality law that compares pressure and volume, we have to get them on the same side. They already are here on the same side. Okay, so we know all of this is a constant, and we get P1 V1 equals P2 V2. Plugging things in, that's 35 times 500 equals 100 V2. You can go ahead and calculate that, and you get V2 equals 175. Now, careful here about the units. We put in 500 milliliters for volume, so we get 175 milliliters out of it. So that is A. On to the third problem here. There's kind of a trick to this one that I'll kind of reveal at the end, but we'll go through and we'll just do it as normal. It says a gas exists with an internal volume of 25 liters at 1.2 atmospheres and 405 Kelvin. What's the new pressure if it has a new volume of 2.0 liters and a temperature of 200 Kelvin? Well, in this problem, we're changing pressure and temperature and volume, all three of them. So we've got to get a proportionality law that relates all three. If we think here, we can arrange it PV over T equals NR. All right, and then the N and the R are constant in this case. So we get P1 V1 over T1 equals P2 V2 over T2. Plugging things in, we get 1.2 times 25 over 405, which equals P2 is what we're trying to find, times 2.0 over 200. Okay, and then we get P2 equals 7.41. All right, and then think for a second here what the units are going to be on that pressure. Okay, you should have realized it's atmospheres. Now look at all of the units on the bottom here. We've got centimeters cubed, liters, liters, and liters. Those are all units of volume, not pressure. And so this is where I said there's kind of a trick to this one. You could have realized that at the very beginning that I had asked you for pressure and I gave you all units in volume. Many people on this problem actually circled A or C when they went through and did it. So, like, be really careful that you're watching the units and that you're thinking about each problem because none of those answers make any sense. So it actually should be E in this case. All right, now for the throwback problem. So there's a whole section where, or a whole worksheet where I go through and explain how to do this more in depth. But the way that this one works, you have to find S and Cl on the periodic table and see how many valence electrons they have. S has 6 valence electrons, so I'll arrange them like this. All right, so they have 2 doubles and 2 singles. The single electrons are open for bonding. Chlorine is a halogen. It's in the second to last row of the periodic table, so it has 7 valence electrons. All right, and then the bonds are going to occur here between the single electrons, and it looks like everything is good here with octets. And so then all you have to do is translate this to a Lewis structure. So it should have Cl, single bond, S, single bond, Cl, and then you have to fill in all of the electrons here. To get full points on this, you have to have it exactly right, meaning the bonds have to be right, the electrons have to be right. You could have a slightly different shape here, like the chlorine could be coming off the top and the bottom of the S, or we could have one chlorine on the left and one chlorine on the bottom, or something like that. But you have to have a sulfur in the middle. The sulfur has to have 2 bonds on it and 2 electron pairs. The chlorines need to be on the sides. The chlorine should have the 1 bond each, and then 3 electron pairs around them. So that's what I'll be looking for on that one.